In this video, we are going to discuss about the linear ordinary differential equation of second and higher order with constant coefficients. Before doing anything, we must know that what is the linear differential equation, means what is the meaning of linear here. So linear differential equation means that all the derivatives which are involved in the equation and the dependent variable must have the power 1. It should not exceed 1. Moreover, their product is not allowed. For example, see this. In this example, you can see all the derivatives and the dependent variable is having power 1 only. So our first condition is satisfied. And what about the second condition? Second condition says their product is not allowed. So we are not having any product of these things because here y is dependent variable, x is independent variable, okay? And though we have the product of x into dy over dx, but for the independent variable this is allowed. Okay, but for the dependent variable this is not allowed. So this is our linear differential equation. Now let's see what is non-linear differential equation. Now here in this example we can see what is the power of this derivative. This derivative is having power 2, which is not allowed in linear differential equation. Okay, and moreover we have product of dependent variable along with the derivatives, right, which is not allowed in linear differential equation. And similarly here we also have product of two derivatives. So this is the example of non-linear differential equation. I hope now this concept is clear. Therefore, the general form of a linear differential equation of order n is this. Okay, so nth order linear differential equation is this, where p1, p2, pn minus 1 and pn, these are the function of independent variable x only. Moreover, this capital X is also a function of x only. It can be constant, or it can be a function of independent variable only. Okay, so because here independent variable is x, so that's why all these p1, p2, pn minus 1, pn, these are the function of x along with this capital X, which is also the function of x only. Okay, or it can be constant. Now let's discuss linear differential equation with constant coefficients. So this is the form of this. So this is nth order linear differential equation with constant coefficient. Here a1, a2, an minus 1 and an all are constants, and capital X. This capital X can be a constant or it can be a function of independent variable x only. But y should not be involved in this x, right? Now we must know one operator, and that operator is operator D. Now dy over dx, we used to write this thing where this d over dx is an operator which is operating over y. So this is just like a function, or you may say it's a machine, okay, which used to take something inside and gives you the derivative of that, right? So instead of using this d over dx, we can use this capital D operator for that. Let's see how. So for d over dx, we'll use capital D, okay? For d square over dx square, for d square over dx square, we'll use capital D square. For d cube over dx cube, we'll use d capital D cube. For d power 4 over dx power 4, we'll use d power 4, okay, capital D power 4. So dy over dx will be written as capital dy. D square y over dx square will be written as capital D square y. dqy over dx cube will be written as d cube y. D power 4y over dx power 4 will be written as capital D power 4y. Okay, this is an operator. Now let's discuss one example. So this is d square y over dx square minus 5 dy over dx plus 6y equal to e power x. So this is second order linear differential equation with constant coefficient, because what is the coefficient of dy over dx? Minus 5. What is the coefficient of y? That is 6. Okay, and here we have function of x only. Alright, now first thing is to use that operator capital D. So this is d square y minus 5 dy plus 6y equal to e power x. So here we can write this as d square minus 5d plus 6y equal to e power x. So this is what? This is an operator which is operating over y. right? So we can write this as function of d also, okay, because this is just a polynomial in d, so we can denote this with f of d, right? This is called symbolic form of your given equation. So this is the symbolic form of what? Given equation. This was the given equation and this is the symbolic form. Now before doing anything, just understand how we'll find the solution of these kind of equations. So complete solution of higher order differential equation with constant coefficients actually equals to complementary solution plus particular integral. Okay, so complete solution will be equals to complementary solution plus particular integral. But let me tell you, if this thing is zero, your particular integral used to be zero. Okay, so if you are having, let's say if you have this equation like this, dy over dx plus 6y equal to 0. In this case, you just need to find a complementary solution or complementary function only. Okay, because particular integral will be 0 in this case. But if here on the other side, instead of 0, you have some function like e power x sine ax, e power ax into sine x or something, then in that case along with complementary solution we have to find particular integral as well. Okay, so in this video we'll just calculate complementary solution, we'll learn how to find this. Okay, so on this side we'll take 0, so whatever the example we'll discuss in this video, on this side you will have 0. Okay, and in next lecture we'll see how to find the particular integral. Okay, now we learn how to find the complementary solution along with one example. So I'll write the steps in this section, okay, and we'll solve the example simultaneously. So the first step is write the symbolic form. So what is the symbolic form of this? That is d square y minus 5 dy plus 6y equal to 0. Okay, so d square minus 5d plus 6y equal to 0, f of d y equal to 0. So this is the symbolic form. Okay. Now what is step number 2? Step number 2 is to write auxiliary equation. And what is auxiliary equation? Auxiliary equation is f of d equal to 0. So whatever the value of f of d you have equated to 0, that will be your auxiliary equation. So here what is f of d? This is your f of d. Okay. So auxiliary equation is d square minus 5d plus 6 equal to 0. Okay. Now step number 3 is to find roots of auxiliary equation. Okay, so find the roots of this. For example, here what are the roots? D square minus, you can just split this into 2d minus 3d plus 6 equal to 0. So roots will be 2 and 3. Okay, roots are 2 and 3. Now on the basis of the nature of roots, we have some rules to write the solution. Okay, that we'll see on the next slide. Now let's learn how to find the complementary solution according to the nature of the roots of auxiliary equation. So before doing anything, I'm assuming that my independent variable is x. Okay, so let's see the case number 1. So case number 1 is if all the roots are real and distinct. Okay, let's assume we are dealing with the second order linear differential equation. So for second order we'll get two roots, and I am assuming those roots are m1 comma m2. Okay, so how to write the complementary solution? So complementary solution is first constant e power first root into independent variable x plus c2 e power second root into x. Okay, for example, let's say if I have solved the auxiliary equation and let's say my roots come out as 2 and minus 4. So both are real and distinct. Then how we'll write the complementary solution? That will be c1 e power 2x plus c2 e power minus 4x, right? Now let's see the case number 2. Okay, so case number 2 is if the roots are real and equal. So if the roots are real and equal, how we'll write the solution? So let's say we have the root m1 m1. So m1 is repeating 2 times. Okay, So we'll assign the same number of constant as of the repetition of the roots. So because m1 is repeating 2 times, so we'll assign 2 constants corresponding to single root m1 along with the increasing power of independent variable. So see how what will be the complementary solution. So complementary solution for this case will be c1 plus c2 x. See, I have increased the power of x, okay, into e power this root m1 into independent variable x, okay. For example, let's say if your roots are 3 comma 3, then how we'll write the solution? c1 plus c2 x into e power 3x. Now let's say if your root is repeating 3 times, means let's say your root is repeating 3 times m1 comma m1 comma m1. Now we'll assign 3 constants corresponding to single root m1. So how we'll write c1 plus c2x. Now we'll increase the power of this x, okay, c3 x square, okay, e power m1 x, okay. For example, if let's say your 2 minus 2 is repeating 3 times, how we'll write the solution? So c1 plus c2x plus c3 x square e power minus 2x, okay. So if you calculate the roots of auxiliary equation and let's say if those roots are real and equal, then we'll assign the same number of constant along with the increasing power of x corresponding to single root, okay. And we'll see one another case. Now let's assume when I solve the question, I got the roots like 2, comma 4, 3, 3. So here 3, 3 are repeated roots, okay, and 2 and 4 are real roots and distinct roots. Then how we'll write the solution? Here we'll apply case number 1 as well as case number 2. So 2 is repeating single time, so c1 e power first root 2x. 4 is repeating single time, so c2 e power 4x. Now because 3 is repeating 2 times, so we'll assign 2 constant corresponding to 3 along with the increasing power of x, okay. So there will be c3 plus c4x e power 3x. So this will be the complementary solution, okay. This is just the dummy example which I have given. Whatever I am discussing here, these are the dummy example just to show you how to write the complementary solution. Now let's see the next case. Now we'll see rule number 3. Okay. So what is the rule number 3? Rule number 3 is if the roots are complex numbers. We know complex roots always exist in conjugate pair. So let's say if your roots come out as alpha plus minus iota beta, then what is the real part of this? So real part is alpha. Okay. And what is the imaginary part? Imaginary part is beta, right? Now how to write the complementary solution for this? Complementary solution is e power real part. What is the real part? Alpha. Alpha into independent variable, that is x. C1 means first constant, cos imaginary part. What is the imaginary part? Beta. Beta into independent variable x plus C2 sine imaginary part, that is beta into x. Okay, this will be the solution. For example, let's assume that your roots come out as 3 plus minus 2 iota. Now what is the real part? 3 is the real part. What is the imaginary part? 2 is the imaginary part. Okay, 2 is the imaginary part. Now how to write the solution corresponding to this? That will be e power 3x c1 cos 2x plus c2 sine 2x, right? This will be the solution, complementary solution corresponding to this pair of roots. Alright, this is just a dummy example. Okay, now let's see the case number 4. Case number 4 is if the roots are repeated complex numbers. Okay, let's assume that your roots come out as alpha plus minus iota beta, alpha plus minus iota beta. So how many roots we have? 4 roots. Okay, alpha plus iota beta is repeating 2 times, alpha minus iota beta is also repeating 2 times. So because we have 4 roots, so there will be 4 arbitrary constants in your complementary solution. So what will be the complementary solution corresponding to this? That will be e power real part. What is the real part? Alpha. Alpha into independent variable x. Now because these roots are repeating two times, so here we'll write two constant, okay, along with the increasing power of independent variable x. So c1 plus c2x, alright, cos imaginary part is beta x plus c3 plus c4x e power, sorry, not e power, sine imaginary part beta into x. Alright, so this is the solution. Now if this repeats three times, let's say alpha plus minus iota beta repeats three times, then here what will be the solution? E power alpha x c1 plus c2x plus c3 x square, okay, cos beta x plus c4 plus c5 x c6 x square sine beta x. So this will be the solution if any pair is repeating three times. Okay, let's see one dummy example. So if you have, let's say, pair 3 plus 2 iota, 3 plus minus 2 iota, and this is repeating two times, then what will be the complementary solution? So complementary solution is e power, what is the real part? 3x c1 plus c2 x cos imaginary part is 2x, okay, plus c3 plus c4x sine imaginary part, what is the imaginary part? That is 2 into independent variable x. Okay, so this will be the solution. I hope this is clear. Now let's discuss some questions for more clarity. Now here given equation is of order 2, okay, and y is our dependent variable and x is our independent variable, okay. So there will be two roots and two arbitrary constant which will be there in your complementary solution. So first step is to write the symbolic form. So d square y minus 3 dy minus 4y equal to 0. So that means d square minus 3d minus 4y equals to 0. So what is the auxiliary equation? Auxiliary equation is d square minus 3d minus 4 equal to 0. So from here, what are the roots? Can I write this thing as minus 4d plus d minus 4 equal to 0? So what are the factors which we'll get? D minus 4, d plus 1. Okay, so from here roots will be 4 and minus 1. So this is real and distinct. So by using the first rule, your complementary solution will be y is equals to, means dependent variable equals to first constant e power first root is 4 into independent variable x plus c2 e power second root minus 1 into independent variable x. So this is a solution. Fine. Now here we have this equation where order is 2. Okay, this time x is dependent variable and t is independent variable. Alright, so here your operator capital D will be d over dt. Alright, so what is the symbolic form here? Symbolic form is d square x plus 6 dx plus 9x equal to 0. So d square plus 6d plus 9x equal to 0. So what is the auxiliary equation? Auxiliary equation is d square plus 6d plus 9 equal to 0. Now find the roots. This is d plus 3 whole square. Right. So what are the roots for this? D will be minus 3, minus 3. So this is the case of real and repeated roots. Right. Real and repeated roots. So for real and repeated roots, we know case number 2 how to write the complementary solution. So complementary solution is dependent variable. What is the dependent variable here? X is the dependent variable. X is equals to C1 plus C2 independent variable, that is T. Okay. Into e power whatever the root you have which is repeating, that is 3 into independent variable T. So this is your complementary solution. Fine. Now let's see the next. So in this equation, we have third order linear differential equation, right? So there will be three arbitrary constants that will be involved in the complementary solution. Moreover, y is dependent variable here and x is independent variable. First thing is to write the symbolic form. So that will be d cube y plus y equal to 0. So from here you'll get d cube plus 1 y equal to 0. Here apply the formula of a cube plus b cube, that is a plus b into a square minus ab plus b square. So if I apply this formula, this d cube plus 1 will be equals to d plus 1 d square minus d plus 1 equal to 0. So from here you'll get d is equals to minus 1, but from here you need to apply the quadratic formula to get the roots. Okay, so I hope that formula is known to you. So this is the formula which we will apply over this. Okay, so here if I apply this, d will be equals to minus of minus 1 plus minus under root b square, sorry not b, here our b is minus 1 square minus 4 into a is 1, c is also 1, 2 into 1. Okay, if I solve this, minus minus plus 1 plus minus under root 1 minus 4 over 2. Okay, so this will be 1 plus minus under root minus 3 over 2. Minus 1 can be written as iota square. So you will get the root 1 plus minus iota under root 3 by 2. So what are the roots? Roots are minus 1 plus minus under root 3 iota over 2. So these are the three roots which we have got. Okay, now how to write the complementary solution? So complementary solution will be y is equals to, first thing is this is the real root. Okay, so first constant e power first root into independent variable, that is x, plus, now what is the real part of this complex roots? So for these complex roots, real part is 1 by 2. So e power real part into independent variable into constant c2, because c1 we have already used, cos imaginary part. What is the imaginary part of this? Under root 3 by 2. Under root 3 by 2 into independent variable x plus c3. Next, sine, again imaginary part, that is under root 3 by 2 into independent variable x. Okay, fine. So solution is this. So c1 e power minus x plus e power 1 by 2x, let me erase this, or x by 2, c2 cos under root 3 by 2x plus c3 sine under root 3 by 2x. This is the final solution. Now this is the differential equation of order 4. Okay, y is a dependent variable and x is independent variable. So because this is of order 4, you will have 4 arbitrary constants in your complementary solution. Okay, so first of all write the symbolic form. So d power 4y plus 8d square y plus 16y equal to 0. So d power 4 plus 8d square plus 16 y equal to 0. What is the auxiliary equation? Auxiliary equation is d power 4 plus 8 d square plus 16 equal to 0. So we have d square plus 4 whole square equal to 0. Alright, this is d square plus 4 whole square. So from here we have d square plus 4, d square plus 4, means whatever the roots you'll get the pair of that. Okay, that will repeat 2 times. Now can I write, if you observe d square plus 4, can I write this thing as d square minus 2 iota square? Let me correct this, 2 iota square, because 2 iota square will be ultimately what? This will be 4 iota square, so minus 4 minus 1 minus will be positive. Okay, so plus 4. Now here apply a square minus b square formula, that is a minus b into a plus b. So what you'll get? D minus 2 iota d plus 2 iota, right, equal to 0. So d will be 2 iota and from here d will be minus 2 iota. So what are the roots? Roots are plus minus 2 iota, and we have this pair 2 times. So that means we got the value of d 2 times. Okay, so these are the 4 roots. Alright, now we are getting the complex roots and these roots are repeated also. Okay, so what we are getting, 0 plus minus 2 iota, 0 plus minus 2 iota. So 0 is the real part. Now how to write the complementary solution? So because we are having 4 roots here, so first thing is e power your real part is 0, 0 into independent variable is x here, into c1, okay, plus c2, because this is repeating 2 times, c1 plus c2x, alright, cos imaginary part. What is the imaginary part? 2, 2 into x, plus c3 plus c4x into sine. Now what is the imaginary part? Let me change the color. Imaginary part is 2, okay, into independent variable x, okay. So this is our solution. So what is the solution? So the complementary solution is e power 0x means what? Something power 0 is 1, so that will be mean 1. So c1 plus c2 x, okay, into cos 2x plus c3 plus c4x sine 2x. Okay, this is a final solution. Okay, you have observed, I hope you have observed that whatever the questions we have done on this side, we are having 0. Okay, so that means we don't need to find the particular integral in order to get the complete solution. Complete solution in this case is actually equals to complementary solution. So this is all from my side. So you can just write y is equals to this. Okay, dependent variable is this. So thank you. We'll see the particular integral in the coming videos. Thank you. So in coming one short video, I'll tell you that how you can check your answer, that whether that is correct or not. And one more thing, how complementary solution is different from the particular integral. Okay, and I'll tell you that what is the importance of those functions which are along with the constant, like c1 e power x or c2 e power minus x. What is the importance of these things? Okay, so I'll cover that short topic in some short video that is just for the knowledge purpose. Okay, so this is all from my side. Thank you very much.